Hey guys, Mrs. Hydrick here with your Atmospheric Systems Objective 1 video. Please take a moment to set up your Wix, and don't forget that if you choose not to write the question, then make sure you answer your essential questions in complete academic sentences. And by the way, we are not going to be answering the questions in order today, so be prepared to do a little skipping around. Here we go. The sun is the source of radiant and thermal energy input for Earth's atmospheric systems. It's the driving force behind many systems on Earth, and one system that we're going to talk about is the water cycle. So as the sun warms up the water on the surface of the Earth, that water will warm up and it will evaporate. It will become less dense because it's warmer, and it will rise up as it evaporates. The upper level wind currents will carry that evaporated water around the atmosphere, and as it moves around it will cool off. As it goes higher and higher into the atmosphere, the temperatures decrease, and so that warmed water vapor will cool off, and then it will change state again. It will condense back into a liquid and form clouds. Eventually those clouds will become heavy with condensation or liquid water vapor, so that liquid will fall back to the surface as precipitation, and that precipitation could be rain, it could be snow, it could be sleet, hail. So there's lots of different forms of precipitation, but the point is that water makes its way back to the surface. It will land on the ground, it will land in lakes, and it will eventually make its way through runoff back to the oceans, where the entire cycle begins again. The water cycle has no beginning and it has no end. It's just a continuous cycle that's been going on for billions of years. Some of the water that does hit the surface will seep through the ground through a process of infiltration to these underwater aquifers, where that water will be stored. And then it could make its way through the ground back to the oceans. Transpiration, just a reminder, is when a plant leaves, opens its pores, and water is released. Kind of like when a person sweats, transpiration is perspiration for a plant. And so this is the water cycle. Please make sure you pause the video, draw your illustration of the water cycle, and don't forget to label all the different parts, especially evaporation, condensation, precipitation. The oceans cover 70% of the Earth's surface. Therefore, the oceans play a major role in the formation and the movement of weather systems. These weather systems could be hurricanes, which we'll talk a lot about, and since the oceans do play such a major role, if scientists study the oceans and the patterns of change in the ocean, then scientists can also make predictions on the pattern of change in the Earth's climate. So the oceans really are a vital component to the formation of weather systems and also the understanding of weather systems. Alright, so we're going to watch this little video on the role of the oceans and the atmosphere in weather.
Earth is the water planet. Although 40% of Earth's population lives within or near coastal regions, the ocean impacts people everywhere. Most of Earth's water is stored in the ocean, a driving force for weather and climate. The Earth's surface is warmed unevenly by the sun. Heat, a form of energy, helps drive ocean and atmospheric circulation. The ocean absorbs and stores more heat than the atmosphere. Both the atmosphere and ocean move heat. The atmosphere does this quickly, the ocean slowly. At the ocean's surface, winds drive forces keep the global ocean conveyor belt, or thermohaline circulation, in perpetual motion. Below the surface, deeper currents are driven by differences in density. Mixing and upwelling in the ocean transport nutrient-rich waters to the ocean surface. Nutrients sustain biological productivity in the ocean. Extreme variations in sea surface height and sea surface temperature affect ocean and atmospheric circulation. El Niño and La Niña occur when changing wind patterns displace warm and cool water in the equatorial Pacific. Both have global impacts. During either of these events, the replacement of cold water by warm water leads to air temperature swings and changes in humidity. This alters weather patterns by steering storms and rainfall to new locations. Shifts in rainfall affect plant growth in areas impacted by drought. When heat is exchanged between the ocean surface to the atmosphere, it influences climate. For example, heat and moisture carried by the Gulf Stream northward bring warmer temperatures and a moderate climate to Europe. An eddy is a circular moving body of water that spins off a main current. Eddies play a major role transporting heat and nutrients. Thunderstorms are a frequent occurrence in the tropics. Some of these may become organized into large rotating systems with strong winds, growing into tropical storms or hurricanes. Tropical ocean basins like the Caribbean and the Gulf of Mexico retain substantial heat, making these regions favorable for rapid storm intensification. By extracting large amounts of heat from the ocean, storms can become massive and destructive hurricanes.
All right, that's where we're going to stop. Just a few important pieces of that video. The sun heats the Earth's surface unevenly, and this uneven heating is really what drives our weather systems. With the equator receiving the most direct light year-round, the water and the air around the equator is going to be warmed up the most, and that heat needs to be distributed around the globe, around the Earth. And so the ocean currents and the atmospheric wind currents play a really important role in moving that heat. The oceans more so because the oceans carry more heat than the air does. And so one way that this heat gets distributed around the world is through the ocean conveyor belt system. This is a system of currents that is moving heat from the equator northward to the North Pole or south to the South Pole. And there's two different currents that make up the ocean conveyor belt system. There are surface currents and there are deep ocean currents. Now, the surface currents are driven by the wind, and these currents are the warmer currents. So they're the currents that you see over here in the picture in red. They're warmer because they move along the surface, which is where, of course, the surface water is absorbing the heat from the sun. So this warmer, less dense water begins to move upward or in the southern hemisphere's case, southward, away from the heat, away from the equatorial region. And as those warm surface currents move away from the equator, they will eventually become cooler and more dense, and they will sink down into deeper into the ocean and become deep ocean currents. These deep ocean currents are driven by differences in density. Because they're cooler, they're more dense, therefore they sink. And these deep ocean currents move towards the bottom of the ocean floor back to the equator, where they will then warm up, rise back to the surface, and this whole process, this whole conveyor belt continues to move. So it's an unending movement of water. It's the transfer of heat from the equator to the poles, and it's a process of these warm surface currents driven by the wind in the deep ocean currents driven by differences in density, temperature, as well as salinity will affect the deep ocean circulation. Speaking of salinity, it's just a measure of the concentration of salt in a body of water. So fresh water is named freshwater because obviously it does not have any salt in it. So the measurement of salinity is 0 parts per 1,000. But as that fresh water through surface runoff makes its way down into the oceans, it's going to increase in its amount of salinity. Therefore, it's going to increase in its density because there's going to be more mass, more matter that is dissolved within a volume of water. And so at that transition area between freshwater and marine, we have water that's called brackish. Brackish water has a salinity range from 20 to 31 parts per 1,000, and anything higher than that is going to be considered marine or salty ocean water. So when we talk about deep ocean currents, salinity is one of those factors that affects the density of the water. So basically, this ocean conveyor belt is a process of convection. Huge global-sized convection cells that are responsible for moving heat throughout the globe. Remember again that the sun warms the Earth's surface unevenly, with areas around the poles receiving the most heat. And so these convection cells in the ocean, their responsibility is to transport and distribute that heat around the world. So we have again our surface currents, which carry warmer, less dense water from the poles, from the equator to the poles, and wind moves those warm surface currents, and they will eventually replace the colder, denser water and sink to the ocean floor as it cools off and becomes more dense, and it will then become a deep current which carries the colder, more dense water along the ocean floor from the poles back to the equator, where it will warm up and rise to replace the warm water that has left. So again, these convection cells in the ocean, they function to distribute heat. Now we do want you to know the difference between a surface current and a deep ocean current. So at this time I want you to pause the video, I want you to draw a Venn diagram, and I want you to fill out the Venn diagram comparing and contrasting surface currents to deep ocean currents. And when you're ready, come back to me. Okay guys, I hope you've spent a few minutes putting together your Venn diagram. I want to take a moment to check and see how you did. Please make any changes or corrections to your Venn diagram or just additions to your Venn diagram based on what we go over here. So both surface and deep ocean currents, they help to move the radiant energy, that's the heat energy, from the sun around the globe. And these currents help to keep the ocean conveyor belt system moving, this distribution of heat from the equator towards the poles. Surface currents are driven by the wind, whereas deep ocean currents are driven by differences in density. That would be a difference in temperature, being colder and more dense, and also a difference in salinity. Surface currents carry warm water from the equator to the poles, whereas deep ocean currents carries cooler water from the poles to the equator. So here are some similarities between the currents and some differences. And again, these two currents make up the ocean conveyor belt, whose function it is to distribute heat around the world because of the uneven heating of the sun's radiant energy on the surface of the earth. And here's a great picture which kind of shows this uneven heating. The equator is right around here, and you can see how areas around the equator in yellow and orange are warmer. It's like a thermal image, so we have warmer water along the equator. And this heat must be distributed around the world. And so the ocean conveyor belt, like the Gulf Stream, carries this warm water over and across the Atlantic, where it cools off and will come back down as a deep cold ocean current. Now, another effect of this warm equator and tropical area is the formation of hurricanes and storms. Because hurricanes need warm ocean water to develop, along the equator and along the tropics, we have the warm water necessary for the formation of hurricanes. So there are a few things that must sort of all come together in order for a hurricane to develop. The first and most important piece is that you have to have that warm ocean water with a temperature greater than 80 degrees Fahrenheit. This warm water will provide the energy for hurricanes and will cause a lot of evaporation. You need that warm and moist air for the formation of these strong storms. So as the water warms, that water will evaporate. It will become less dense, and of course that water vapor will be forced up as a result of the lift that comes with rising warm air and warm water vapor. And so that lift will go up, and then it will be blown outward by these upper level winds, which just allows more to come up and lift. So the outward flow above the storm allows more and more air and more water vapor to rise up, which just helps to strengthen our hurricane. And then we also need to have light winds on the outside, light horizontal winds on the outside of the hurricane to help steer it and to allow it to grow. Because if our winds are too strong, then they will literally just cut the top off of the hurricane and the hurricane will not form. This is a thermal image of Hurricane Katrina. And remember, here, oh, there we go, there it is. A hurricane is nothing more than a low pressure storm system. We've learned that as warm air rises up, it leaves an area of low pressure. And so hurricanes are low pressure systems that grow over the water, and they become really severe storms. And we can determine how severe a storm will be by sending a hurricane tracking planes that will fly into a storm to measure the pressure. And the lower the pressure is within the center of the storm, they then know the stronger that storm is becoming. And so here is an image of Hurricane Katrina, and since this is a low pressure system, the circulation around the center is in a counterclockwise direction, and so this hurricane is circulating this way as it makes landfall, and it did make landfall right into New Orleans. And so the center is your area of lowest pressure, and the intensity of the hurricane is strongest near the center, and as you move outward, the bands become less. In this case, it doesn't really look like it's less, but the winds are less severe towards the outer bands of the hurricane. And so again, hurricanes are storm systems that develop over the equator and over the tropics, and they're steered by these upper level winds, and so make sure you get all of those factors as characteristics on how hurricanes intensify and grow. Okay, guys, that's it for me today. You have your support item, though, which is to compare and contrast the climate for London, England, and Seattle, Washington, which are both at the same latitude, but they have different ocean currents running alongside. You have your warm ocean currents running alongside one and a cold current running alongside another. So research which city has which current and how those different temperature ocean currents will affect their overall climate. All right, guys, I'm out.